zeros and graphing. A polynomial function has real and or non-real zeros. And we talked about that in the last lesson. The real zeros correspond to the x-intercepts of the graph. They're very useful. The x-intercepts, where the graph crosses the x-axis. We talked about multiplicities in the last lesson, but a multiplicity describes a specific appearance on the graph. And so if your multiplicity is 1, then the line crosses. Okay? It crosses the graph kind of like, it kind of looks like a straight line. It kind of looks like y equals x, or x to the first, if you think about it. Okay? It's going to cross just like that. If you've got any even power, like a power of 2 or a power of 4, okay, multiplicity of 2, multiplicity of an even number, it's going to bounce. And what I mean by bounce is it's going to look like a parabola, or y equals x squared. Okay? It bounces like x squared bounces. If it's odd but different than 1, we can call that a wiggle. And a wiggle is going to look like this wiggle, like y equals x cubed. Okay? So the multiplicities on our zeros kind of give us a description of what the graph's going to look like. We can look at a graph. So here are some graphs. And you ought to be able to look at the graph and say, okay, here is a 0 at -2. Okay, everybody see there's a 0 at -2. And here is one at +2. And here is another 0 at +4. Everybody should be able to see that. Okay, label that. -2, +2, and 4. But you should also be able to tell me the multiplicities of those. Okay, the multiplicity of the first one, you know, look at, would you say that this looks more like y equals x? Or more like y equals x squared, or more like y equals x cubed? Well, I think it looks more like just y equals x. It just crosses. And so I can see that this has a multiplicity of 1. When you look at the second 0, it kind of looks like a parabola shape right there. If you just zoom in right around that dot, it looks kind of like a parabola. And so I can tell that the multiplicity on that one is 2 because it bounces like a parabola bounces. And then the next one, if you zoom way in, you'd have to zoom way in. It pretty much just crosses. That's not a wiggle. That's just a cross. Okay. And so I see a multiplicity of 1. Now, why that's useful is you're going to have some questions that talk about factors. And if I had to factor, I can see that that first 0, remember the 0 value of -2? The 0 of -2 would come from a factor of x plus 2. Since it's a multiplicity of 1, I know I just have one factor of x plus 2. But then you've got the 0 value of +2 must have come from a factor of x minus 2. But with multiplicity of 2, that means it got repeated. So there's x minus 2 squared. And then a 0 value of 4 must have come from a factor of x minus 4. With multiplicity 1 just means it's there one time. Okay? So I can see exactly what the zeros do and exactly what the factors do based on those multiplicities. So then we look at the next example. I can see a 0 value at 2 and 4. But if you look at their actions right around those, this one is a wiggle. Okay? That one's a wiggle. So I can see that the multiplicity is odd, but not 1. Okay? So I'm not really sure if it's a multiplicity of 3 or 5 or what. I can tell it's an odd number, though, that's different than 1. And then here, that looks pretty much straight. So that looks like a multiplicity of 1 right there. So if you had to factor it, this thing might look like x minus 2 to the third power and x minus 4 to the first power, like that. Okay, but again, I don't really know if that's a 3 or a 5. I don't know that odd one exactly. I just know it's odd but not 1. Okay. Turning points, polynomial function of degree n has at most n minus 1 turning points, with at least one turning point with between each pair of successive zeros. Students kind of struggle with that, but if you're talking about like an x to the 4th function, that means it has at most 3 turning points. Okay, that's what they're talking about. So if I said f of x equals x to the 4th plus blah, 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 that would have at most 3 turning points. And what I mean by that is it's going to look, it might look like a W or something like this. And turning points is where it goes from it was decreasing and now it's increasing. That's a turning point. And then here it was increasing and then it goes to decreasing. That's the second turning point. Decreasing turns to increasing. That's the third turning point. Okay. Now it doesn't say that a degree 4 has 3 turning points. It says a degree 4 has at most 3 turning points. So, be careful there. It doesn't necessarily mean it has to have n minus 1 turning points. It's just that's the most that it could have. The end behavior of a polynomial graph is determined by the dominating term. The dominating term is the one with the biggest power. All right. The one with the biggest power is usually in the front, but doesn't necessarily have to be in the front. So the dominating term for this one is a n x to the n. All right. Usually it's the first term. So once we know the dominating term, we can determine the end behavior, and the end behavior is going to be one of these 4 pictures. Okay, you look at that first term, and let's say you have like 4x to the third. When this number is positive and you have an odd, so you've got positive and odd. We've got end behavior that looks like this. Okay, down and up. And there's dot, dot, dot in the middle because we don't really know what happens. All right? We don't really know what happens. So I sometimes I'll pretend like those are my arms and act like those things are my arms, and you've got a head and you don't really know what's happening in the body, but I call that a disco function. Okay. You've seen, I don't know if you've seen, it's pretty old, but John Travolta doing this disco dance where one arm's up and one arm's down. Okay, disco function. So that's positive odd. If you had a negative odd, you just reverse it. So reverse disco right there. If you have a positive and even, you can think of like a touchdown. Okay, the referee puts his arms up in the air, and that's a touchdown function, a parabola. That's a positive even. But if it's a negative even, you put your arms down. Okay, so we've got down and up. We've got up and down. We've got up and up, or down and down. That's the end behavior. And again, it's called end behavior because we're not really talking about what's in the middle. We don't really know what's happening in the middle. But we can tell the end behavior pretty quickly. For instance, example 2, use the symbols for end behavior to describe the end behavior of the graph of each function. Well, this is the dominating term. So notice it's a negative even. If we know the dominating term is a negative even, then we know it's going down and down. Dominating term is a positive odd. Positive odd. I think since it's positive, I kind of think of it like slope. If slope is positive, it goes uphill like this. Okay, so I'm thinking about my disco has to go uphill like that. Okay, down and up. That's a positive odd. This one is a negative odd. So it's a reverse disco. I think of it like going downhill slope. It's going to look like this. And then a positive even. That's the touchdown function. That's like a parabola, up and up. Now, we like this end behavior. It's useful for when we have to graph because we want to sometimes draw a quick sketch. And that end behavior is going to be useful for us just picturing what this thing looks like. And here are some steps for drawing a quick sketch. Graph in a polynomial function. Step 1, find the zeros. Find the zeros. We might be able to factor, or we might have to use synthetic division like we did in the last lesson. Those are your x-intercepts, okay? The real ones are anyway, not the imaginary ones. We don't know how to graph those. Step 2 basically just says plug in 0. Plug in 0, this is the y-intercept. I plug in 0 because it's easy, but that's the y-intercept. And then step 3 covers a lot of stuff. We use the end behavior to decide what this looks like. Okay, is it a disco function? Is it a touchdown function? Whatever. Then we look at the multiplicities and whether the graph crosses, bounces, or wiggles. And selected points means basically just make an XY table. So they're giving us kind of a way to figure out how to graph polynomials as quickly as possible.